Hello and welcome to this edition of the Science Avenue, where we will explore the concept and fundamentals of SETI, the search for extraterrestrial intelligence. Since late 1940s, inhabitants of planet Earth been hearing stories and seeing footage of alleged UFO or extraterrestrial sightings. Unfortunately, all these stories can be described as some form of hoax, natural phenomena, or anything but UFOs or ET. But beyond hoax or science fiction, what are the chances that other civilizations exist in our galaxy? The search for extraterrestrial life is as old as humanity itself, with evidence gathered from many civilizations around the world, from Camonica Valley in Italy to the Nazca Desert in southern Peru to Mesopotamia. These records are in the form of drawings engraved in stone or clay and could be the work of imagination or records of actual events. In the modern age, SETI is relying heavily on radio telescopes in particular. A visual spectrum telescope, such as the Large Binocular Telescope, or LBT for short, is using mirrors to magnify the light received from celestial objects. The biggest shortcoming of this type of telescopes is that they are only equipped to receive visible light, which is a very small fraction of the electromagnetic spectrum. A radio telescope, on the other hand, is equipped to detect signals invisible to the human eye, such as X-rays, gamma rays, infrared and ultraviolet emissions. All waves dissipate as they travel across the vacuum of space, and radio waves reaching the surface of Earth are so weak that currently various telescopes around the world are working in a coordinated fashion to detect the most distant and the smallest objects, such as planets orbiting nearby stars. A planet orbiting a star will cause a dimming in the light detected by the radio telescope. The magnitude and the frequency of the dimming in light can determine the size of the exoplanet and its proximity to the host star. The atmospheric content of the exoplanet is determined by spectroscopy, where infrared emissions received by the telescope is broken down into color bands. Wavelength of the different color bands is an indication of the presence of certain elements or compounds, such as water. Now that we have a basic understanding about how radio telescopes work, let's dig in a bit deeper into the philosophy of SETI. And the first name that comes in mind is Enrico Fermi. Credited with the design of the first nuclear reactor, Fermi wondered if alien civilizations exist. Why can't we detect them? If aliens had spaceships that could travel at 1% of light speed, the galaxy could have already been colonized many times over. This is known as the Fermi's paradox. To help answer Fermi's questions, in 1961, astronomer Frank Drake came up with an equation to estimate the number of detectable extraterrestrial civilizations that might exist in our galaxy. Each variable is an important factor for the development of intelligent life. The number of civilizations with interstellar communications capability calculated by multiplying the following inputs. The number of the stars born per year. According to NASA, this figure stands at 7 stars per year. The average number of habitable planets per solar system. A planet in a habitable zone is not too far or too close to its host star. This zone is also referred to as the Goldilocks zone. Planets are common in the universe, but a small fraction of these planets are located at the right distance from its star. The chance of a habitable planet to develop life. The odds of a planet to develop life appears to be very slim. According to our knowledge today, planet Earth aside, no life have been detected anywhere in the solar system or beyond. The chance of life developing intelligence. This possibility is proven to be extremely remote. Among millions of species. On Earth, only humans are considered intelligent, although chimpanzees, dolphins, crows, and some species of octopus show signs of very basic intelligence. Chances that intelligent life developing the capability to communicate across interstellar space. It is logical to think that some alien civilizations can be xenophobic or simply not interested in interstellar communications. Finally, the length of time that a civilization survived to send signals across space. Our recorded history is less than 10,000 years, and we have developed interstellar communications less than 80 years ago. During this time, we've been through a world war and a nuclear Cold War threatening to annihilate life as we know it. Punching in Derek's numbers into this equation yield 10 technologically capable civilizations in the Milky Way. Given the vastness of the galaxy, it is conceivable that we are entirely alone in our region of space. The solar system and all the planets that we can detect fit inside this small circle. In 1964, Russian astrophysicist Nikolai Kardashev established a theory where civilizations can be categorized by their technological capability to harness energy from their surroundings. According to Kardashev's scale, Type 0 civilization is one that have not yet harnessed the full energy potential of its home planet. Humanity is at 0.73 on the Kardashev scale. Type 1 is a civilization capable of harnessing the full potential of its home planet. That includes the widespread use of nuclear fusion and renewable resources on Earth. We might be here in just over 100 years. Type 2 is an interstellar civilization capable of harnessing the full energy potential of its host star. This would include megastructures around the star, colonizing the entire solar system, and even harvest asteroids and comets. Type 3 is a galactic civilization capable of harnessing the entire energy potential of its host galaxy. This type of civilization could be easily detectable, but no evidence been found so far. Kardashev's emphasis on energy consumption is logical, but not the only method to classify a civilization's technological prowess. If you have other ways to categorize a civilization, please share your thoughts in the comment section. The James Webb Telescope is due to be launched in October 2021 and will provide us with valuable information about the atmospheric contents of the exoplanets. But what have we found so far? Before its retirement on December 2018, Kepler Space Telescope provided a great opportunity to find habitable worlds within 1,000 light-years from Earth. Most notable is K2-72e, located 217 light-years from Earth in constellation Aquarius, with size slightly larger than Earth and an average temperature about 6 degrees warmer than Earth. K2-72e is orbiting a red dwarf in a tidal lock, which means that one side of the planet is constantly facing the dim star. Kepler 1649c is a confirmed rocky planet orbiting red dwarf Kepler 1649, located 301 light-years from Earth in constellation Cygnus. Discovered in April 2020, Kepler 1649c is almost the same size of Earth and is receiving 75% of its star's heat in comparison to Earth, enabling this planet to theoretically maintain liquid water on its surface. Kepler's replacement, the Transiting Exoplanet Survey Satellite, or TESS for short, discovered TOI 700d, an Earth-sized rocky planet orbiting the red dwarf star TOI 700 every 37 days. The significance of this discovery is that the magnetic field of TOI 700d is expected to be very similar to that of our planet, increasing the likelihood of atmospheric retention. Perhaps TRAPPIST-1 is the most interesting star system to be detected in the search for habitable planets. Located at a relatively close distance of 40 light-years from Earth, in constellation Aquarius, TRAPPIST-1 have 7 planets located very close to each other. 3 of the planets are located in the habitable zone, all Earth-sized planets. I believe if there is an interstellar mission in the future, constellation Aquarius, where TRAPPIST-1 and K272e are located, will be the most likely destination. Many thanks for watching, and if you found this video to be interesting, please share and subscribe.